there was some homework that was due in the interim and was extended, and the homework was to produce a listing of the basic blocks in a piece of code. And you've all, I believe, turned something in, which is great. I have downloaded all your solutions, but I have not run the grading stuff yet, just because I've combination of first not feeling well and then being overloaded with other stuff. But I will get it run and get those entered. Let's talk about, I want to talk about the vector registers, just a small amount. And it's, I think a good way to motivate this is to talk very briefly about something that you will see in assembly, which is loop unrolling. And it may look kind of weird to you, and so I thought I'd just go through it really quickly. Nothing super fancy about this. And actually, after this, I want to go back. I'll go through my solution to the homework, which I should have done a minute ago, but I'm kind of scattered this morning. All right, loop unrolling. So over on the right-hand side, there are two pieces of code. They both run through 10,000 elements. The top one does them one at a time. The bottom one does them two at a time. And the question is one better than the other? And you probably already know the punchline to this, which is that, yeah, it turns out that one is potentially better than the other. And here's what they might end up looking like in assembly. This is just sort of notional. We'll see what they actually look like in assembly in a moment. But this lets us talk about what's actually happening. So over here, it may not seem like there's much of a difference, because you do this line 10,000 times, or you do this line 5,000 times and this line 5,000 times, and there's an add in this line, an additional one. So what's the benefit? Well, here's how they might turn into code. So you set RCX equal to 0. You have the amount that you're adding, because all of these add some increment into each element. And then you run through adding that increment into each element of an array. You increment RCX, you compare it to 10,000 to see if you're done. And if you're not, you jump up here to the top and you go through the loop again. This is a jump less than. So if the result of this comparison is that RCX is less than 10,000, it'll go back up to the top. And so each time through this top loop, you do 1, 2, 3, 4 instructions. And you do it 10,000 times. So about 40,000, this turns into a sequence of 40,000 instructions. Down here, you do the same setup. You also add this into this element of the array, and then you add this into the next element of the array. And because they are, I guess we're assuming 4-byte integers, we add a 4 to get to the next one. We add 2 to RCX, and we compare it to 10,000. If not, we go back to the top. So here we do 1, 2, 3, 4, 5 instructions each time through the loop, but we only go through the loop half as many times, 5,000 times. So that is 25,000 instructions. So that's 40,000 for the top one versus 25,000 for the bottom one. In addition, we only do this compare and branch down here 5,000 times. We do it 10,000 times up here. And comparing and branching, as I think I have mentioned, is frowned on. You want to do that as seldom as you can, because it destroys your instruction pipeline. So here's some C code again to do this. So we can compile this little C function and see what the compiler makes of it. And this is what it makes of it, right? It takes this little simple piece of code that we have right here, and if we just straight up compile it, we get this. And there's a couple of things worth pointing out. One is that this is your standard way that code is laid out by a compiler when you don't optimize. It assumes that you want everything copied back to a well-known temporary space, in this case on the stack. All right, here we go, and here we go. And because of that, it's going to be slow, right? Ideally, this is all going to live in the level 1 cache, but it might not. Okay, and so you might have some initial loading of pages or other foolishness that goes on. Another thing to notice is that we're writing a bunch of stuff onto the stack, right? Here we are at RBP -4. So that is the first open slot on the stack. Here we are at RBP -14, RBP -20, etc. And do you ever see anywhere where we reserved room on the stack? And in fact, we didn't, right? Here we push RBP, move RSP and RBP, and then we don't do any stack reservation. We just start adding stuff on here. And you might remember why that's okay, right? There is something called the red zone that exists on the stack. It's not anything magical. It's just a convention. And we say that, the first chunk of bytes on the stack can be used for scratch stuff. And it won't be, we guarantee it won't be overwritten by an interrupt handler. That's important. But we can only get away with using it because this is what's called a leaf function, right? This function doesn't call any other functions. If it did, they might come along and try to use the stack, and that would be a problem. So we would actually then need to reserve some space on the stack by moving the stack pointer. So we would say something like RSP gets RSP minus, what would that be, 28, x28. And then we'd be okay, and then we would restore the stack down here, which they don't do. Another thing I was pointing out, they've saved the stack pointer in RBP, but they never push or pop anything, so the stack pointer never changes. And so once again, it's not removed down here. It's just the way this ended up being done. So a few other little things to note. There are some no-ops living in here, right? There's one and there's one. And I think these are just to align this on an 8-byte boundary. Why? I don't know. It's not the target of a branch. It's just some wasted space. So they went ahead and optimized away, modifying the stack and restoring the stack. And then they inserted some NOPs just for fun, I guess. I don't know. Anyway, this is not unusual in terms of the kind of code that you see. And this is great for a program debugger that wants to associate lines of code with instructions in your program and associate locations primarily on the stack with local variables. This is going to be great for debugging, but it's going to be awful for performance, as you might guess. We have all of this code here to do this, and that's going to be terrible. One last thing to point out is CDQE. What is that? Well, we go ahead and we get a value and put it in EAX. And the value that's over here is actually increment. How do I know that? Let's go back up here. The first argument is increment, and it's a 4-byte int. The second one is an array of ints. So I expect this first one to be a 32-bit integer, and this one to be a 64-bit pointer. And I know this one's going to be in RDI, and this one's going to be in RSI. So if we look, we'll see that there's EDI, that's a 32 bits, gets put on the stack here. And RSI, which is the pointer, gets put on the stack here. And then we have a local counter, 0, which gets put on the stack here. Okay, so double word goes on here. And then we put a double word here, and then we put a pointer here. And then whenever we need those, we'll have to go get them out of memory. So down here, we go and get the current counter and put it in EAX. It's an int. And then we call CDQE. So CDQE does just like the mnemonic says, so obvious, it does a signed extension of EAX into RAX. So clear. Actually, you see this a lot, because EAX is 32 bits. If I want to use it to reference something in an array like I do right here, this needs to be 64 bits. But what if EAX is a negative number? Well, then the 64-bit version isn't going to be right. It's just going to be a big unsigned number. So what I want to do is then copy that sign bit all the way across the other the high 32 bits. And that's what CDQE does. It replicates the sign bit from the lower 32 bits all the way across the high 32 bits. So now if this is negative, it remains negative, and I can do my stuff correctly. So that's what CDQE does. So each iteration of this loop, we can count, right? Here is the test, and if the test is works, and we jump all the way down here and do the compare. This is what a while loop looks like when it's sort of poorly assembled, and we jump up here. Each time through, we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 instructions. We do it 10,000 times, so that's 170,000 instructions. That's not great, considering that just 2 slides ago, we got away with 25,000. So clearly this is not optimal, but this gives you a good sense of the compiler just sort of laying out lines of code directly in here with stuff stored straight in on the stack, and a leaf function and a few other good things to point out. What if we optimize it? If we optimize it and just use -O, that's a -O2 is usually what I use when I'm getting ready to try to look at something, but -O will work just fine. We get this. This is way, way, way better. Does it do the same thing? It sure does. We add a value to something pointed to by RSI. We add 4 to RSI. So instead of using computations to get to it, we're just adding 4. So we're marching through the array. We compare RSI to RAX. It's a little bit odd. And we jump, if not equal, up to 10. So this does 1, 2, 3, 4 instructions each time through the loop for a total of 40,000 instructions to accomplish that. So back here, previous one, we had a counter in this space on the stack. That counted up, and then we compared it to our end value, 270F. Yeah, so it's 10,000 minus 1. So we're looking for it to be, so we just add right here. We add right here, and so it makes sense to compare it with the lower. We start at 0, so we'll compare it to the lower right after we add. So we're looking for that. If it's jump, we jump if it's less than or equal. So on the last one, on the 9,999th one, we still jump up here, and on the 10,000th one, we fail and fall out. So it's a little weird how it decided to do the loop controls, but nothing too weird, right? This is a counter, and it counts up to this value plus 1, and we're good. Here it doesn't do that. It does something else. How does it determine when to stop the 10,000 element loop? Well, we see that we're doing a compare of RSI and RAX, right? RSI, we know, must be the pointer to the element in the array. And so we need to be comparing this to the end of the array. How do we do that? Right up here, we do a load effective address of RSI. Now, what's RSI on start is, go back to the code, this, right? This is RDI, this is RSI. So this is a pointer to the array, it's the start of the array, and then we add 9C40 to it. Well, that's not what we had last time. 9C40. Well, look at that. That is 40,000. It's not 10,000, and it's not 9,999. It's 40,000. Why is that? That's because every element of the array is 4 bytes long. And so this would actually be the first address not in the array. If that makes sense. If the array contained a single element, that would be at offset 0, and we would want the ending address to be 4, because that would be the first address past the end of it. And so here we set it to be 40,000 past RSI. None of this should be strange to you or seem weird. Here's a no-op. What's that no-op for? Alignment. So we have a nice 8 or 16 byte aligned top of a loop, because that's good for performance. And then again, the 4 instructions, and do that 10,000 times for a total of 40,000 instructions. There we go. Pretty straightforward, I think. We can test it. So we'll write a little harness. The little harness will come in here and it will populate the array with random variables, or random values, sorry. And then it will then update every element of, it will update the array by adding this to every element, and it will do that 10,000 times because computers are fast. So in order to be able to measure this, we're going to have to make this work a lot. And so it'll do a lot of work. Now, the optimizer will throw all this code away because we're not modifying anything that persists outside of this function. So to prevent that, we return entry 0, which makes the optimizer think entry is actually being used, and so it can't throw it away and it has to preserve it. So we might expect, based on what we've seen, that we'll get a speed up when we go from a single step at a time to 2 steps at a time, and that speed up should look right around 4 1/4 times speed up. And that was based on, way back for this one, sorry. That was based on looking at these and thinking about the time through here and the fact that we only do the branch like half the times in this one that we do up here. So the pipeline should stay full. So we can sort of guesstimate we should get about a 4 1/4 times speed up. What do we actually get? We actually get about 7 times speed up by unrolling the loop once. We go from 676 milliseconds down to 93 milliseconds. As you can easily imagine the impact that would have if you're doing some big computation, or you're trying to do ray tracing or some other kind of thing on the processor. Big savings. Are we done? Well, here is the update with the loop unrolled once, and we can compile that, and this is what it looks like. And that will, unrolling it will cut our time in half if we do it that way, and that's fine. But the unrolling it by hand is kind of a pain, so we can also ask the compiler to unroll it. Yeah. So we have this -f unroll loops, funroll loops. So we funroll them, and the compiler decides that the right thing to do is to unroll it 1, 2, 3, 4, 5, 6, 7, 8 times. So there's 8 of these. And this is a NOP at the top, so don't be misled by that. There's 8 of these. 8? That's weird. Why would it be 8? Okay, fine, whatever. Again, it computes the end position. It adds 20 to it each time, a hex 20, that's 32, which is, of course, 8 times 4, okay? And so it's going to count by that. It compares it to the end, it jumps to not equal up here. This was all generated by our faithful GCC. And when we run it, it's almost exactly the same result as we got when we explicitly unrolled it just once. So there you go. So not much of a savings of unrolling it more times. Doesn't really help you that much. The returns diminish. Are there other ways we can speed this up? Yes, there are other ways to speed this up. And in fact, a good way to speed it up is to use vector registers. So I've mentioned XMM and YMM and ZMM in the past. They have their own instructions. They can be a little unusual or cumbersome to use because they don't work exactly the same way that other registers work. There's some little funny differences, but that's okay. They have basically their own set of instructions for dealing with them and for working with them with other registers, and you can read about how to do that, and it's not anything too complicated. Doing the loop using these registers results in a big savings. I get it down to just 10 milliseconds to do all of that. So that's really good. That's getting down to a performance that would be, about the best we can do. I can cram more into a larger vector register, but it's actually, again, I'm going to have diminishing returns. So here we go. Here's my little code I wrote. So I take EDI, which is the amount that I'm going to increment, and I do a move D, because I'm putting a double word into XMM2, and then I do a shuffle. So shuffle is an instruction that allows me to populate one of these registers in various fancy ways. And in this case, what I really want is I want the XMM registers hold 128 bits. And since each double word is 32 bits, that's basically 4 double words. And so what I really want to do is do a double word shuffle, which copies this value into all 4 of the slots of that register, and that's what this does. And so I wind up with EDI in all 4 of the double word slots of XMM1. So think of XMM1 as a vector of 4 copies of EDI. I do a load effective address. Again, I'm doing the same thing the compiler did. I'm picking the stop address. So I take RSI, which is the start of the array, add 10,000 to it, and put that in RCX. And then later down here, I'll compare RSI to RCX. And as long as they're not equal, I will jump back to the top. So then I go into the loop. And so I take RSI, I go get the contents of RSI, and I move that into XMM0. So now XMM0 holds the 4 double words starting at that address, right? And it's doing anything fancy to do that because I just read out 16 bytes of memory, right? 4 double words. Double word is 4 bytes. 4 times 4 is 16. I just read out 16 bytes of memory and put it in here. How did I know to read 16? Well, that's how big this register is. But also right here, I told it what I wanted to do. And so it gets copied in here. So now I have the next 4 elements of the array in this register. I have 4 copies of EDI in this register, and I just add. Now there's a ton of different ways to do this add. What I want to do is be sure that if it overflows, it does the right thing. And so I use padd, and you can go and look that up, padd, which is double words. So it knows how long the things are in here. And so it knows where to carry and where not to carry. All right, enough of that. Then I need to write this back. So I had to read into here, and now I've got to write back. And if you've ever done any RISC programming or ARM programming, this will look like a very familiar pattern. Right? I take something in memory, I put it in a register, I do something to that in the registers, and then I write back out to memory. That's a very common pattern on reduced instruction set machines like the AVR and the ARM. So XMM0 now holds the updated 4 values of the array, and just write it straight back to RSI. So I used a move DQU up here. So you would expect me to use a move DQU to put it back, but nope, that's not how things work. So I use a move UPS, and there we go. Now it's back. I add 16, right? Because I dealt with 16 bytes at a time. So I add 16 to RSI, do the check, and I'm done. There you go. It's actually, sounds complicated. It's actually fairly simple. And when you do this, you get really good performance. And as you note earlier, the compiler did not do this. It didn't do this with all the optimization settings we had, and I don't think it will generate it unless you explicitly, and maybe I switch to explicitly tell it to do this. But a lot of times, processor manufacturers introduce new instructions, introduce new types of registers, and it takes a while for compiler writers to catch up. Whew. There's a lot. Before we get into this, though, I promised I would go through my solution to blocks. So that's in here. So let's do that. Probably not. Still not feeling super great, but I'm definitely feeling better. All right, the basic Python 3 startup at the top. Find the basic blocks in an ELF library. A lot of the usual imports. I don't know that it's changed much. And then I have a class. Okay, we'll come back to that. Let's go down to the main function and take a look at that. So here's my main function. And it has lots of return statements in it. And so I disable the pylint warning about having too many returns. Because as you see, I have all these error checking conditions, and each one of them has a return, and that will make pylint mad. It'll think the code is too complex. And it's not, this is not complex code. This is just a bunch of checking for error conditions. I could have used a flag or something else, but this is way simpler and easier to look at. So there you go. So I make sure I have the right number of arguments. And if I do, I open the file. And you'll notice I use the class I mentioned earlier. I use rad to do that. And we'll take a look at rad in a few moments. Basically, rad is random access disassembler. We'll see that in a moment. It just handles doing the disassembly stuff for me, packages it up. So then I come down here and I look for main, and I just call find main, and I pass it my little disassembly guy. And it does exactly what we did previously. It runs the same algorithm the same way, tries to find main, and returns it in start address. If start address is none, then there was an error, and I return 1 and stop. If start address is 0, then I couldn't find main, and I go ahead and get the entry point, and that's it. That's the start address. So I'm done with this little if. I've checked for errors. If I didn't find main, I've set my start to the entry point, and I'm ready. So then I do pass 1 of the 2 pass process. Pass 1 is implemented by this little function, pass 1. I give it my little thing that does disassembly for me, and I give it a set that is initialized to just contain the start address. So this is the only leader. So the way that pass 1 works is you give it one of these, and then you give it a leader. And based on that, it tries to find other leaders, and it returns to you a set of leaders as its result. If I get back none, there was an error, and so I'm done. I stop. Otherwise, I tell you how many leaders I found, and I do pass 2. And I pass in rad again, and I pass in the set of leaders I got up here, and this writes them out. And at that point, I've done everything I'm supposed to do, and I return. This is the boilerplate to start main. So let's go take a look at rad. So here's rad. It's pretty, I don't know how straightforward it is, but it's not anything too complicated. Let's scroll to there. So I have a static method which constructs an instance of rad from a file. And because I'm currently defining the rad class, the Python type checker will tell me that rad is not already defined. And as weird as it seems, this is how you get around that. This works. And the type checker understands that and correctly checks it. That's crazy, I know, but that's how that works. So this method is going to take a file name, and it's going to construct an instance of rad and give it back to me. And the way it works is pretty simple. It's going to open the file. It's going to wrap it as an ELF file, and then it's going to return, it's called the constructor of rad, passing the ELF file to it, and return that. But what if exceptions happen? What if there are exceptions in here? Well, the documentation explicitly says, here are the exceptions you should expect. You should handle those. So here's the constructor, or not the constructor, underscore underscore new underscore underscore is the constructor in Python. This is actually the initializer. Python separates them. We're using the default constructor in here, but you could override it if you wanted to. You can read about that if you're curious. There are occasionally reasons to override the constructor itself. but not here. So here we just want to initialize, and we have the self object that comes from the constructor, and we have elf, which is the elf file instance we passed in right there. So now we're going to initialize this. And so we go ahead and do get section by name to get the text section. If we get back none, we raise an exception and terminate. Otherwise, we set self data to the text data, the data of the text section, self start to the start address, self end to the end address, which I get by taking start and adding the link of the data to it. I go ahead and create one of these guys, right? This is the thing that builds disassembly generators. So I create one of those and I store it here as _CS. The underscore, by the way, is a way to say this is private data. Python has no real notion of public or private data, but by convention, the underscore indicates private data. So I set detail to true. I go ahead and get the entry point address, and then I save the elf file in case I need it later, which I won't, but I save it anyway. Then I do this. I create a cache, and I set it to be a dictionary mapping from integers, addresses, to instructions. So I'm going to cache the results of the disassembly in a big associative array. It's going to do that because it's going to result in much better performance. And then I populate the cache. So I call a little private instance method called populate cache, and I give it the start address, and I tell it, go ahead and populate the cache. And then I tell you what the entry point of the little text section is. So, and then I'm done. This sets up, this initializes all of the local fields of my little self object. Once I'm done with that, next thing to look at is what happens when I populate the cache right here. What do I do? So I come in here and tell you I'm repopulating the cache. I set a limit equal to 100, which probably is too low. I probably should have used a much higher number, but that's okay. And then I iterate, I go ahead and start disassembling. And I disassemble in data, and notice I figure out the correct offset to the address where I want to start. And I take the start address, subtract that from address. That gives me the offset into the data array. And the address associated with that 0th element of that new slice is adder. So I pass all that into disasm, and I iterate over the instructions that come back. I check to see if the address is in the cache. If it is, I've hit a place where I've already got addresses, already got instructions cached, and so I stop. Or I check to see if my limit is reached 0. If it has, I stop. In either of those cases, I stop. Otherwise, I go ahead and add that instruction to the cache, and I decrement the limit. So populating the cache just goes ahead and grabs the 100 instructions at this address and adds them into the cache. And initially, that is the start address of the text section. There we go. This may seem weird, but believe it or not, this has a big boost in performance for this whole thing. A larger number probably would have yielded a bigger boost. I think I set it to 100 because I was actually looking at some code that has data bytes in it. And so this gets off and you sort of waste some cycles. And so setting it to a lower limit results in less of that. But that's a weird case. Getting the entry point returns the entry point to me. So I just return self entry. Is in range lets me determine if an address is in the address range associated with the text section. And this is a good chance to show off something that Python has that not a lot of languages have, and that's chained comparisons. There's address right there in the middle, and I'm checking to see if start is less than or equal to address, which must be less than the end. And this works. And this gives me a Boolean, which I return. So I can call in range with an address, and this will return true if it's in the text section, the address is in the text section, and false if it's not. So that takes us to dis. Dis is where the disassembly actually happens. I give it an address, and it gives me back a generator, just like when I call disasm. And in fact, that's how it gets it. It calls disasm. This is all typing information. If you're not typing your program, don't worry about it. If you want to know how to type your program, then this is how you do it. Generators are weird, and so they have 3 type arguments associated with them, and there you go. But this is going to return instructions. So I check to see if self is in range, address. So I want to be sure this address you've given me is in range, and if it's not, I throw an exception. Otherwise, I do this loop right here. I do a while true. And this is my generator. This right here is basically, it builds a closure and returns it to you as the generator. Why does it do that? Because it contains a yield. Right there it is. So if you ever master generators, they're incredibly useful things in Python. So I check to see if the address is in the cache. If it is, that's awesome. I just return what's in the cache. Right? I grab the instruction out of the cache. I add the length of the instruction to the address. So now address is pointing to the next linear instruction. And I yield the instruction. I hope that makes sense. So yielding means basically the generator returns the value to you. When you call next on it again, you'll come back into here, and the next instruction after the yield is basically the if again. And so I would do this again to be sure the address that I just updated was still in the cache. I would get the instruction, and I would yield it, and I would just keep yielding instructions out of the cache each time through, because this is while true, until something's not in the cache. Well, what happens if the address is not in the cache? Well, then I would come down here and I would see if the address is still in the text section. And if it's not, I break out of the loop. When I break out of the loop, that tells the system the generator is exhausted. We're done. And so if you were using a next, or if you're using, just try next on it, you'll get an error, you get an exception. If you're using it in a loop, this will terminate your loop. So there you go. So I check to see if it's in range. If it's not, I break. Otherwise, it's not in the cache, and it is in the text section. So I populate the cache from that address. And I have a little sanity check here, which is probably incredibly unnecessary. I don't know why I'm doing this, but I do it anyway. But basically, I populate the cache from that address. And then that's all I do. I don't yield anything. I go around the loop again. The address is now in the cache, and so I yield it to you. And that's how it works. That's my little disassembly thing that returns instructions to you and populates the cache as needed. Whew. All right. I hope that's somewhat clear to you. The only thing that might be weird about it is the use of yield, but just think of this as a place where we halt this loop, save a closure. You should know what a closure is, you're computer science students, and return this to you. And then the next time you call next on it, we go back in the closure, we do the next instruction, which happens to be going around the loop again and doing this again. We just keep doing this until you don't want any more instructions, or you exhaust the generator with these breaks and terminate. All right, that's it. That's my random access disassembly code. In previous classes, I've written it to be able to find an address in any executable section and disassemble from there, but that leads to more complexity, and it's already complicated enough, so I thought I would stop with this. Quit while you're ahead. All right. So now I have a little routine called get basic block. And this should be pretty simple, right? You just, I give you access to the disassembler. That's the guy up above. I give you the address at the start of the block, and I give you a set of leaders. Why do I give you a set of leaders? Well, because a basic block ends when I hit a jump or a return or a halt or a loop, or I hit another leader. So I give you those, and I'm going to give you back a list of instructions that constitute the basic block. I think the optional is overkill. I don't think I ever use that. I think I always give back a result here. Okay. So extract the basic block. I go ahead and disassemble, right? Rad.dis calls this disassembly thing, gives me a generator for disassembly at the start of the block. I set my basic block to be the empty list. For instructions in this, I append the instruction to the block. I compute the address of RIP for that particular instruction, right? That would be the address of the next linear when that RIP would be set to. And I check to see if it's in leaders. If it is, the basic block is done, and I break out of the loop. If it's not another basic block leader, I get the mnemonic. And if it starts with J, then it's a jump or a J less than equal, whatever. Or if it's in this, I'm putting jump in here as overkill because it's already here. So yeah, more code optimization. Or it's in return, red I, halt, or loop. If this condition is met, I'm done with the block and I break. That's it. And so when I am done, the instructions for the basic block are accumulated in the block, and I return the block. That's get basic block. I don't think it gets much simpler than that. Find main, you've already seen, and it doesn't change much, except now I'm passing this in instead. And so instead of directly working with capstone, I work with this, which is nice because all of the capstone stuff is now encapsulated in this RAD class. So if I were to try to use another one of the myriad disassembly libraries, there'd be one place where I would need to go change it. So that's how this is going to work. Here's the explanation of it. It's just going to find main. So we get the entry point. We go ahead and get the basic block at the entry point. That was easy, right? We just go ahead. I want to get a basic block, so I give it rad. I give it the entry point, which is the address to start from, and I give it the set of leaders we already know about, which is none. And so I give it an empty set. If the block is none, I return none, right? This means I had an error happen. There's an exception or something else that happened here. And so I return none. And as you remember from main, if I return none, the whole thing stops. So then for fun, I print out the basic block. And so I check to see if debug is in debug. If it is, then I just use debug statements to print out the whole block. I check to see if the block ends with the call, with call followed by halt. And so I make sure the block is long enough that my indexes won't cause a problem. I pop off the last instruction in the block. I check to see if the mnemonic is halt. I pop off the next instruction and I check to see if it's call. And so if there's too few instructions, or if it doesn't end with call followed by halt, I have to think backwards because this is the last one, this is the next to last one, then doesn't match the pattern, and I return 0 because it's not an error. It just means that I couldn't find main. And that leads to the case in my main program below where I look for 0, and if I don't find it, I set it to the entry point. Whew. I think hopefully that's pretty straightforward. And now I do the other stuff I did before, basically the same loop I had previously. I'm going to march through looking for something that sets RDI. So I'm going to go ahead and work backwards, just like I did last time. Get the mnemonic. If it's a move, I'm going to see if it is a move into RDI of an immediate value. if it's an LEA, I'm gonna make sure that it's a load effector address into RDI of a RIP relative address, and I compute that. And that's it. And I return main address. We went through this last time. So here's pass one. Pass one is the complicated piece. Pass one is where we go and find all the basic block leaders. And how do we do that? We do it just like I said many times. We give you RAD, we give you the initial set of leaders, which probably just contains the entry point or the address of main. And I give you back an optional set containing integers, addresses of leaders. Optional here, if you're not familiar with it, that's just like, I'm trying to think of what it's called in some other languages. Basically, it says, you're going to give me back none, or you're going to give me back a set. This is a union of a set of integers and none. So returning none is fine. That will type check because I did tell you it was optional. Okay. So if there are no initial leaders, I have nowhere to start. And so I immediately fail and return none. You didn't tell me where to start looking. So it's not my job to go find the entry point. It's your job to go find the entry point and pass it to me. So I give up. Otherwise, I initialize my stack. Remember, I said you might want to use a stack for this. So I initialize my stack to be a list of the leaders, right? This is a set. I turn it into a list by just wrapping it with list. Python is so nice. And now I do something a little bit weird. I define a function right here inside my other function. Okay, what does this function do? The nice thing about defining local functions like this is they generate a closure around the local variables. What are the local variables? Stack leaders. So this function can access them directly. And in fact, it does, right? We'll see there's leaders being accessed, there's stack being accessed, etc. So I'm going to call this whenever I want to push something onto the stack to explore. Now, I don't want to explore something if I've already explored it. I can end up in an infinite loop in that case. So what I do is I make sure that the address you're giving me is in range. This is where I'm going to check for that. So I find a candidate leader and I just push it. Well, what if it's outside the text section? If it's outside the text section, push won't do anything, right? It'll determine that it's out of range and it will stop. And I make sure the leader is not already in the set of leaders, right? If it's already in the set of leaders, I've already looked at it. I don't want to look at it again. And so I don't add it again, right? So I have this set leaders is the one that comes in here, and I'm going to modify it. And then stack is what I need to explore, and hopefully that will eventually be empty and leaders will be full, right? So I'm going to empty the stack and fill this up as I'm doing it. And this is how I push. All right. With all that out of the way, here is my loop to do the exploration. While the stack is not empty, do this stuff. When you're done, return the leaders because you found them. Pop the leader off the top of the stack, which would be the last element of the list. And go ahead and get a disassembly starting at that leader. And now I just iterate over the instructions in that disassembly because most code is linear. So I'm just going to just walk over it. If something changes that, well, I will break out of the loop and I'll come around again. If the stack is not empty, I'll pull it out and I'll begin exploring again. So if the address is, and I did toy with the idea, by the way, of using get basic block here, but I decided not to. I decided that would be a little bit too cutesy and I'd rather just show this. All right, so if the address is in the stack, then I remove that address. What? Well, it's possible that an address can be pushed onto the stack more than once. I didn't check that up in push. So now that I'm about to explore it, I go ahead and get rid of any copy of it that's on the stack. Would it be better to check for that up here? Probably, maybe. I don't know, maybe. But I didn't. I checked for it here. That seems good enough to me. I now look for new basic block leaders. So I get the mnemonic. I get the value of RIP, because I'll need that to compute RIP relative addresses. I check to see if I have a call or a jump. Right. Either one of those, I want the immediate operand. And if I have an immediate operand, then I push it on the stack. Okay, that's kind of it. That is a candidate leader. Now, if it's a call, I want to keep going. But if it's a jump, I want to stop because that's the end of the block. And so I just check to see if it's a jump. And if it is, I terminate the for loop. And I'm out of the for loop and back into the while loop. And I check to see if the stack is empty. If it's not a call or a jump, I check to see if it's a loop or something starting with a J. Can't be jump. I already tested for that. So it has to be a condition code, JCC or JXX, if you want to think about it. Jump less than or equal to, jump, carry clear, etc. If it is, then I go and get the operand. I want it to be immediate. I push that onto the stack. And I also push RIP on the stack because I might fall through and do the next instruction after the loop or the branch. So I push both of them on the stack here. Now these terminate the block. These terminate the basic block, but all of them do. So I just immediately terminate my search in the basic block. I break out of the for loop, go back into the while loop while the stack is not empty and go around again. Otherwise, I check to see if it's in return, ret I, or halt. Those all terminate the block. They don't add any leaders. So if I hit one of those, I just break. And that's it. That's my pass one loop. Go find other leaders. Pass two is not complicated. I give it this guy and I give it the set of leaders and I print them out. And so I make a new list called leads, wrapping my set. I sort leads in ascending order, and then I iterate over all the leaders that are in leads. For each one, I get the basic block using my get basic block function. If the block is none, then I had an error. And so I tell you I had an error. That would be an internal error because that should never happen if I write the code correctly. But I should check for it anyway. And I continue. And then for each instruction in the basic block I got back, I print out the instruction. Then I print a new line because they're supposed to print a new line between each block you print. And that's it. That's my pass two. I just print them out. And that's all of it. And it works fairly well. Let's pick something, which it takes about, for something fairly large, like Bash, which is about a megabyte. It takes about 3 minutes, I think. It scales nicely linearly. I've run it on a whole bunch of different stuff. But let's not waste 3 minutes looking at that. Let's go ahead and look at something simpler. Let's look at LS. So run it on LS. I think that's small enough that it shouldn't take a long time. And there we go. And you can see here's an NBR. A good sanity check is if an NBR shows up in the middle of one of your blocks, you're probably wrong. And your block should all end with the normal thing you expect: a jump, a return, a jump if equal, right? So here's this one, and then the following instruction is right here. So this is the following basic block. And we can work back through it, and they should all be about right. This one is a little funny one right here. What's happening here? What's happening here is that somewhere somebody wants to jump to this. So this guy jumping to the return ends up being a basic block leader. So I had to terminate this basic block because I hit a basic block leader. And anything else worth pointing out in here? Probably not. A few more returns where we jump to a return. That's not that uncommon. And there you go. And so we've reduced our, in this case, LS program down to a nice set of basic blocks. And that'll be important for the homework that is to come. We've exhausted an hour. Why don't we stop now and take a 5-minute break, and then when we come back, we'll go back into looking at type-based decompilation. Actually, before we do that, are there questions about my solution to the blocks problem?
Have you posted blocks? I didn't see you if you posted that yet.
I haven't posted my solution yet, but I'll post it after this. I will post it as an attachment to the new homework.
Okay, I think. Okay.
Yeah.
I don't have a question about blocks. I actually have a question about loop unrolling in general. I'm not sure if you. I may have missed you saying this, but isn't the issue with loop unrolling, at least on modern processors, is that it's actually faster just to do the smaller loop more? Because if you unroll a loop that's more memory, you have to have loaded at a given time.
So you have to go through the memory anyway.
Right.
The reason that it saves you on modern processors is because modern processors do so much predictive execution.
Oh, okay, it's because of prediction.
Yeah. So again, they are trying hard to fill their work schedules with whatever you're giving them, and a lot of them predict that branches will be taken. That's they make up. There's a lot of literature about how to do like stochastic prediction, other ways of doing this, and a lot of times it comes down to the branch is probably going to be taken, so we should assume we take the branch. And if it recognizes a pattern like a loop like this, then it can go ahead and fill its work schedule with the following instructions. But the timings I gave you for these were based on running it on this machine, which is a 64-bit AMD. Not super fancy. You can see it's an older one. It's the machine I use for this. But I got similar timings on the other machine next to me, which is a much more performant machine.
Right.
And it's an Intel. I want to say it's a i7, I think. So it's a pretty modern processor, and you still get basically the same timings, just a little faster.
Yeah. Okay then. Thank you.
Sure. Other questions?
I have a question about your solution to the blocks.
Yeah, sure.
In LS, when you had it, your solution up there, I saw a call in the middle of a block. I thought it was like the leader, so wouldn't that have to be at the start of a block?
It's not in this one. Did I already drop out of that? Hold on. Let me go back to. I wonder if I saved it. I have not. Let's look at one of these. So what were what was the thing you're looking for?
The call with the address is just in the middle of the block there, so like line 4 or 5.
Yeah. So here's an example of that. Yeah, the call doesn't end the basic block.
Well, I think I understood that it was a leader, so I think in my code, my solution, I had it as a into a block because it is the start of a new one.
That's okay. I'm not gonna complain about that. In fact, in previous classes, I've usually had a switch, which lets you say whether you want call to end the block or not. But the normal way that call works is you plow down through here, the call happens, it does some work, and it comes back, and you keep going. And so it's rare that you would, that most software today that breaks your code up into basic blocks like Ghidra and those doesn't end the block when you hit call. And
Okay.
so I've just kind of quit doing that. It results in a little easier to understand code too when you're structuring it.
Okay, that
Now the
makes
call
sense.
didn't have to come back, right? It could be, right? This call right here goes off and never returns. It is entirely possible. And it's possible for a number of reasons. It's possible this call could trigger the process's exception handler, and you could unwind it. It could be that the call immediately pops its return address and then does its own thing. I mean, especially in malware, it's kind of dicey. What you see call in malware, you're usually thinking, what are they doing? Are they calling something, or are they doing some weird thing, right? So it could be that you want to end the block there, but the same thing would be true for syscall, right? Syscall, we could treat as an ender to the block, but you seldom do because you expect the syscall to come back, and we already know for a fact that some syscalls don't come back. And so what you traditionally do is follow that syscall with a halt to indicate that this one is not expected to return. But okay, so I hope that answers your question.
It does.
Sometimes the blocks do end with a call here. That's just happenstance, right? This one happened to be the instruction right before another block leader, which is right here. So somewhere somebody is jumping here or branching here or calling this address or doing something else. And so this block had to end because it ran into the beginning of a new basic block.
Okay.
All right, other questions about anything?
If we used your when the solution to main you gave us that we could use for blocks, if we used your find blocks function, would we be we should have been fine on getting the correct block back, correct?
I assume so. I'm trying to think what find blocks. I'm trying to think what it does.
It's the one that it's the define method you have for like getting a basic block based on an address.
Oh, okay. Yeah, that seems reasonable.
Yeah, okay. I was making sure because I looked, I realized I went to check to make sure I hadn't myself done something weird with with call before realizing it was your find block thing I had used, which doesn't stop on call. But when I'm looking for addresses, I do note call, but that doesn't necessarily stop me from doing more.
That's right.
So I think I'm fine. I just wanted to make sure.
Oh, yeah, that's right. And there are probably some ways I could have simplified the code. I think I could have gone ahead and used the get block or get basic block function again in pass one and abused it in that way, and that might have led to some smaller code. But it's you don't want to be too tricky or too clever.
Okay, I looked back at my code and I ran it again, and I don't think I have an issue. It was just I was worried for a moment I'd stopped on a call for some reason before realizing no, I had the only reason I'm looking at call specifically is I'm looking for call addresses.
Yeah, okay.
So I think I'm fine. And by the time I'm actually looking at basic blocks, I've already checked all the calls, so I shouldn't be stopping on them anyway. But yeah, thank you for.
So which echo? So I really recommend using. I haven't already beaten on this. Let me go ahead and type that to most. I really recommend using debug. Debug is really pretty handy. So I use the daylights out of this thing. So debugging is enabled. Here's my argument. Populating the cache. That's good to know that actually happened. Here's my entry point. Text section is given by this range, right? This is inclusive and this is exclusive. Opening the file, populating the cache. So the cache gets populated again. Here's some stuff that happens. I look backwards. Here we go. I'm starting with stack depth 0. And you see I'm wandering through here, and you see a few other little populating the caches pop up because I've branched somewhere I need to populate the cache. And stack depth is now 15. So you can, if you're having weird conditions, you can see how deep your stack's getting. Stack depth is 9. Going down to the end. Here we go. We're it doesn't work in here. So Go back to the end because now it's just printing. There we go. So stack depth is 0. I got some stuff here. Oh, then I have a jump, so I got to add some leaders. So adding a leader, I then pop those. Those have probably been explored. Stack depth is still 0 because they've probably already been explored. But I have one leader to pop off here, potential leader. I'm done. Found 127 blocks. So super useful stuff and does not pollute the space. All right, so 5-minute break. Let's do that, and I'll meet you back here in 5. Type-based decompilation. So the paper is up on the iLearn site. Have a look at that. It's some heady stuff. Let's get into it. So this is really about decompilation. And the Mycroft paper is sort of a seminal paper in being able to solve some of the challenges you have when you're trying to understand what's happening in a program because you're decompiling it or because you're trying to do a smart disassembly or you're trying to do program analysis. And basically, decompiling a program requires that we rebuild a lot of the semantic information that was present in the source code. And that usually means guessing, right? Because that semantic information has been lost. And there are many programs that can be compiled to yield the same object code. And one of the main things that gets lost is the meaning of what's being stored, what's being held, right? I see RAX, and I don't necessarily know if that's a pointer or an integer. That was one of the problems we had with Steensgaard. We had to sort of just make a guess about that. And we have to do the same kind of thing here. So we have memory shapes. What does a portion of memory represent? Is it an array? Is it part of a linked list? What is it? And again, figuring this out is going to make use of types. Type theory is just a ridiculously useful branch of computer science that is only appreciated by compiler writers and people who write code that analyzes programs. I think that's pretty much it. And maybe theorists. But it's really, really useful. Okay. So the goal is decide what a part of memory is. Is it an integer? Is it a pointer? Is it a structure? And the way to do this is to observe how that memory is being used. Okay. So the paper is type-based decompilation and program reconstruction by type reconstruction. And this paper was written by Alan Mycroft, who it turns out is one of the founders of the Raspberry Pi Foundation. So if you've used a Raspberry Pi, this is the guy over here who helped to create that. So he's going to describe a system which decompiles C programs. It doesn't have to be C, but he's going to focus on C for a lot of obvious reasons, from machine code by type inference techniques. C is a great language for this sort of stuff because C has the trappings of a high-level language while not actually really being a high-level language, while being a fairly low-level language. So the trip from assembly to C is less drastic than the trip from assembly to many other high-level languages. There's a lot of things that are just, you can just sort of directly code them out and say, here's the C code for it. In fact, there's a whole school of decompilation that basically maps instructions to C code and then does optimization of the C to try to generate decompilation. And that's pretty much not happening anymore because that turns out to be a terrible way to do it. But that was, not an unreasonable path to take early on. Okay. The algorithms remain independent of the particular architecture. Well, that's great. How do we get there? Well, we treat the target instructions as registered transfer specifications. Aha, he's going to start talking about RTL. Now, we've talked about RTL before, but he's going to come at us with his own simplified RTL. So target instruction gets transformed to RTL, to register transfer logic or register transfer language. Don't care what you want to call the L. And then is transformed into SSA. Well, we know what SSA is. That's static single assignment. There you go, the SSA form. And he even points out that undoes things like register coloring. What was register coloring? We talked about it. That was, I maybe had an example where you might of using this. Once I've figured out, I've done my static single assignment, and I figured out what's live and what's not live at each point in the program. I then want to assign values to registers for performance. And it turns out, perhaps I can use RAX for 3 or 4 different variables in my program, and it will just work out because they're live at different times. And figuring that out is doing register coloring. Okay, that figures out the way in which I can store things in registers. And that's undoing this is important because if I'm going to figure out how things with memory is used, I need to have a single meaning for each of the different values that might be in there. If sometimes RAX holds C and sometimes it holds, the start of the linked list, then I need to know that. And so I have to undo the coloring effect, and static single assignment will do that for me. This then generates a set of type constraints. So again, we're constraining, not necessarily giving you a single solution. Same as with Steensgaard. Recurring themes here. I'm going to use the type system. I'm going to use it to generate constraints about it. I'm going to use a lot of the stuff that you've already seen to make that work. And there you go. So iteration and recursion over data structures causes synthesis of appropriate recursive C structs. What does that sentence mean? What it means is when he sees iteration or recursion, different kind of iteration, over a data structure, he's going to create a recursive struct to deal with that. Close my doors, getting noisy out there. Okay, and this is triggered by and resolves something called occurs check, which we'll look at, constraint violation. So those of you who've had classes in symbolic logic will already look at that and know what occurs check is. The rest of you will cover it. Other constraint violations are resolved by C's casts. So we're just going to cast things because C has casts. It's very convenient. And unions. So unions are a part of the C language that has sort of fallen out of widespread use, I think. It used to be super common, especially when you're writing low-level code. So I've written a lot of, because I have a misspent life, I've written a lot of device drivers and I've written a lot of embedded code, and unions are really, really the thing, they're critical to making a lot of that stuff work. I want to be able to take a big chunk of bits and just, throw some bytes in it, right? I read some bytes off the wire or off the disk or out of memory or somewhere else, and I just throw them into this array of bytes. And then I want to turn around and say, you know what, this is actually a 64-bit value followed by, some 32-bit values, followed by a 16-bit value, a byte, and another 16-bit value. And the union lets me do that, right? I can union a big, array of bytes and a struct, and then I can access the stuff in different ways. And in fact, it gets worse than that. Sometimes you have different kinds of, let's say, packets coming back to you. on some of these protocols. And the packets have a fixed length, so you can just throw them into your union. But then you look at the first byte, and that tells you how to interpret the packet. And so then you have 3 or 4 different ways to interpret it, and you have 3 or 4 different types of structs, and the union is over all of those, and it just works beautifully. But it can lead to some really funky looking code. If you've not used unions before, it's just a way to say, hey, this thing might be one of the following types. It's a union over types. If you think of a type as being the set of all the things described by it, so the type int is the set of all 32-bit 2's complement integers, or a linked list node is the set of all the things that satisfy those constraints. Then you think of this as the union of those sets. So in the limit, what is the limit of what? Well, he's going to constrain, but not determine. He's going to try to resolve constraint violations. In the limit, we use heuristics to select between equally suitable C code. So we're going to constrain, but then we might have a case where we just don't know. We've done all we can do, and we now have a couple different possibilities. Maybe it's a pointer, maybe it's an integer. It could be either one. We actually can't tell. So I'm just going to make a choice and plow ahead. Okay. He says, you know what? You got to build a GUI to do that. Right? Here's a good problem for some grad students. Go build a GUI to do that, to facilitate the professional use. So here we go. This is what he's going to give us. He's going to give us a way to take a program, go through RTL, through SSA, identify what structures are, how they're used, and that's going to tell us what those structures are. And in the event that it does not, we're going to just make a guess, make a reasonable guess. So something worth pointing out before we get too deep into in the midst of this is to think a little bit about what a compiler is doing and what decompilation is doing. So here's my original source code, which I'll just call P. Okay. And it's going to produce a binary program, which I will call Q. So P generates Q. I'll think of this as, I probably use the turnstile something here, but from P, I derive Q. And I'm throwing information away, right? I have a lot of information in P, and I'm throwing a lot of that away when I generate Q. And so that tells me that this is many to one, right? Many different programs over here could be compiled and optimized down to the same bytes, making up the binary program. What that means is that this function is not invertible, right? I can't go ahead and given Q, generate the original input program because I have literally thrown information away. Sometimes I throw a lot of information away, right? Like you saw how I completely optimized away a loop in a previous class. Well, that's not great. What I could do is I could maybe say, well, here's my Q, and I can generate from it maybe the set of all programs that yield Q. So I generate equivalence classes over here. All the programs, 2 programs, A and B are equivalent if they both compile down to Q. It gives me an equivalence class and a partition of the set of all programs. The problem with that approach is all my equivalence classes are infinite, right? Because I can always throw code in that gets thrown away, right? I can always add more code that will be optimized out because the compiler thinks it doesn't do anything. And I can just add, arbitrary copies of that. So it's not super helpful to try to think about that. What we might do is think about going from Q to some other program, P prime. This is our decompiled program. Okay. And it would be great if we could take P prime and compile it and get Q. What that would tell me is the program P prime was in the correct equivalence class over here, right? I took a program P, I generated Q, but then I managed to somehow yield back a P prime that was equivalent to my original program. That would be great, right? That's what we see over here. And that's why this is double direction, right? The idea would be P prime can be compiled into Q, and Q can be decompiled into P. That's great. That's this round trip property of decompilation that is not a thing. It's unfortunately not really a thing. It's hard. There are many different compilers, and there are many different compiler settings, and there are environment settings, and there are processor settings. And so if I compile source code on my machine and you compile it on yours, we may get, for the same source code, we may get different things. And that's just, a fact of life. In fact, it's such a problem that there's this whole movement about repeatable builds, right? I build the program and I get something and I make a tweak to it to fix it, but I build it again and I get something completely different. And that's weird. I don't like that. So repeatable builds are the idea that I should be able to get the same Q every time I compile P, get the same one out. And it turns out that's not non-trivial, because again, computers are hard. And it's also the case that this is hard. If you look at the decompilation that a really state-of-the-art, powerful decompiler like Yeeter gives you, you'll see that in a lot of cases, you can't compile that code. It's not proper C. It's got stuff in it that's not going to compile correctly, or it doesn't compile back to the original program. And that's just, this is hard. This is hard stuff. But this is sort of the ideal. It's what we'd love to have in the ideal. It's what we're trying to get to, because there's a lot of really cool things we could do if we could make this work. All right. Not the least of which is we could actually use this kind of a trick to build better decompilers. That may seem crazy, but it is in fact true, right? Because I could now take a program, I could map it then onto an exemplar of that program. And that's pretty powerful stuff. That means I could take a piece of open source code, generate its exemplar, and then I could search online to see if anyone is cheating and using my code. But unfortunately, we can't do this. Purely hypothetical. So another aside, he mentions something that is a really important piece of computing history. And it's such an important piece of computing history that it's worth taking a few minutes to talk about it. Some years ago, the folks at Cambridge were busy creating their Cambridge programming language. Now, if you ask them, oh, it's combined programming language. No, it was the Cambridge programming language, CPL. And this language had tons of features. It was a very feature-rich language. It was so feature-rich that it was nearly impossible to build a compiler for it. Another example of that problem is the language Ada. So I don't know if anyone out there has ever worked with Ada. Ada is an amazing, wonderful language. Back in I did some work with Ada back in the 90s. And it was sort of like a language that had arrived from the future. It had basically every feature you could imagine in it. Some that were really cool, but it had terrible compilers. It had terrible compilers. So it was object-oriented. It had this powerful module system. It had the ability to dynamically recompile stuff. I mean, there's just really amazing stuff built into this. And it's still being used. It's just the compilers were so dreadful because it was such a complicated, such a big language. I don't think complicated. It was just a lot going on in it. Tasks, it had the ability to do asynchronous tasking long before that was built into any other language. Really, really good stuff. And CPL was kind of the same thing, tons of features, but it made it almost impossible for anyone to build a compiler for it. So they decided what they would do is they would compile from CPL to something called basic CPL. And then you could go from basic CPL to machine code. So the idea was basic CPL would be something that was high level enough that you could get there from CPL, but also low level enough you can get to assembly from it pretty easily. That sounds to us now like a register transfer language. It's not what it was, but that was kind of the idea that they were circling. And so they call that BCPL. And BCPL worked. It worked really, really well. And the most important thing about it is, in a world where everyone's building new and different computers that have different instruction architectures and different word links and weird features, it was easy to port. So if you wanted a language to run on your computer, so a high-level language, so you could write programs in this high-level language, you could get BCPL onto your computer pretty easily. Now, because of that, this was an incredibly influential language. And we'll see just how influential in a few minutes. If you've never heard of it, that's a shame. Cambridge programming language is a dead language. The punchline is, this was awesome, and they never built this thing. That's not true. I think around 2008 or so, they actually finally built a compiler for this. I mean, they just sort of abandoned it, and then years later, the compiler was built. BCPL lives on. In fact, you can still get compilers for it, and it mainly lives on in the form of the C programming language, right? That's where C comes from. That's the heritage of C. So what was in BCPL? This was the first brace language, right? It used curly brackets to denote blocks of code, or you could use this if your keyboard didn't have these symbols on them, because again, early days, weird computers, weird keyboards, we're still trying to figure this stuff out. This is the first time anybody wrote a Hello World program. And the first one ever we can tell was written in BCPL. What did it look like? It looked like this. And this ought to not look too weird to you. You might be a little put off by some parts of it, but you can see that we go and get a header. That's good, because the header is going to define things like write F. Looks a lot like printf. Yeah, doesn't it? So then we say, let's start, which is a function, be the value of these brackets. So this is just a way of defining that. And we do this write hello world, and then the result is 0, return 0. So there you go. That's your first canonical hello world program. That's the hello world program. It introduced the / comment form. There you go. That's where it comes from. It used a virtual machine and bytecode. So it beat Java to the punch by some decades. It didn't have any types. Everything was a word. And it was platform dependent. So that can be a little problematic, right? If your platform has 16-bit words, or 32-bit words, or 12-bit words, then the programs are going to be a little different, but that's okay. It was also the first major use of Hungarian notation. Okay, so what in the heck is that? So no types. That means if I see X, I don't know what X is. I have no type information associated with it. But what if? And remember, BCPL was intended to be the intermediate stage. So type information was in CPL, but it was lost when you went to BCPL. So they didn't think they needed to build type information into it. And so when you wanted to write a program, you, the program author, you need type information to help you manage the complexity of your program. And so what you would do is you would add prefixes and suffixes to variable names in order to know what they meant. A common one was to put P in front of something for a pointer. So you would say like PX, which would indicate that X was a pointer. Another common one was to put SZ on the end of a variable. So like name SZ, or PSZ name would be another way to do it. PSZ would be a pointer to a zero terminated or null terminated string. So PSZ name, sometimes it goes on the end, most of the time it's on the front, and there you go. So it's ways to encode type information into variable names. If you've never seen that in programs, great, you've lived a good life. We have type information now, and hopefully you don't have to have that. Compilers were small. The compiler, I want you to think about this just a minute. The compiler for this guy, with keywords and all the stuff it has to do, some compilers could fit in 16K of memory. I challenge you to write a hello world program on Linux that fits in 16K of memory. That's your challenge, right? The whole compiler fit in 16K. It spread to support 25 different architectures before it gradually gave way to C, which was, BCPL with types. It was the first language used on the Xerox Alto. Now, if you don't know what the Xerox Alto is, you've again had a terrible computer science education, because this is an unbelievably influential piece of hardware, right? This was the first computer that was designed for working with a GUI, if you don't count the mother of all demos, and you have to Google that, mother of all demos, where basically in the 50s, the guy laid out the entire history to the modern day of computer science. Absolutely incredible. You should totally watch it. So BCPL was succeeded by B, just B, and then by C, right? What comes after B? C. What comes after C? C++, and nearly everything else. So D is a language. D owes its heritage to this. Java derives from this. All this stuff came about because of BCPL. It's just barely older than I am. The first compiler was written in 67. I was born in 68, and so I'm old. And there you go. So I've never written any BCPL, but I have seen code written in BCPL, which was running on some old machines. An aside, nothing I'm going to test you on. Just this is the kind of stuff that you hopefully find interesting, and is it useful information? I don't know. If you're going to be a computer historian, maybe, but it's always good to know where this stuff comes from. And a huge amount of the stuff that we're using today comes out of this language. RTL. So he's going to use RTL, and where do the first RTLs come from? Well, they come about in 1980. So here you go. This is 67, right? No notion of an RTL. BCPL is going to be their intermediate language, their RTL. It's going to take a while before we get to actually coming up with a way of doing this, of having RTL. And it originates in this paper, which is a seminal paper. Again, another very, very important milestone in computer science: design and application of a retargetable peephole optimizer. You'll have to read the paper to find what that is, because I don't want to get into it now, because I've already taken too long with this digression. But really, really important stuff. You'll find it here. So register transfer language basically lifts processor semantics to a more abstract level. So instead of saying RAX has 64 bits and we're putting this value in here, we say, I got a register of some kind. I don't know what it is. I have an infinite number of registers, and I'm going to put a value in one of them. Okay. This is commonly used in compilers. In fact, it's used in, I can't think of a compiler that doesn't use it, because they're all based on the LLVM stuff, or on another well-known compiler framework like Rose or one of those. And they all use RTLs to get their work done. So the idea is you compile source code to RTL. So everybody knows how this stuff works. And it's moderately high level compared to the target architecture. And so if you want to build a compiler, you build your compiler to compile your source code into RTL, into the RTL for whatever you're using. And then somebody else has built the system that translates RTL into the target architecture. There are challenges to this, obviously. If I compile my source code to RTL and just write that piece and I don't worry about the underlying architecture, I can drop information out that causes the rest of the system to be unable to properly optimize my code. I'll give you a specific example, which I talked to you about earlier for this particular reason. I give you that big loop, I compile it down to RTL, but I've lost information. I might want to have hints in the source code that you should use vector registers for this. And if that gets dropped out of here, then there's no way for you to know that you should do that when you build the target. So RTLs really have to be, in the ideal case, they are a pure abstraction, right? You throw away the architecture and you invent a hypothetical language with infinite registers and basic operations, and you compile everything to that. In reality, they have to be polluted by information that you have to carry on through so that you can do this piece well. All right, enough ranting about that. And there's tons of them. All right, why are we back to this? I'm sure I had a good reason to come back to this, but I can't think of what it was. All right. So in Mycroft's paper, he opens by saying, let's consider an intuitive example. And he gives you the code right here. This is a function called f, and it does some stuff. And probably by now, some of this will look normal to you. Mul, XOR, return, you'll recognize those. ld.w, what is that? That's loading a word. And then you'll see R0 and R1. Those are registers. Okay. So, and you can probably guess what's happening here. This is similar in some ways to the AT&T syntax. It's just the way it is. What may be a little more confusing is some of these have 1, 2, 3 arguments, right? XOR has 3. That's because you have 2 sources that you XOR together and a destination, right? So this would take R0 and R1 and XOR them and store the result back in R0. This multiplies R0 by itself, so it squares it and stores the result back in R0. So to go quickly through this, he just invents registers as he needs them, R0, R1, R2 ad nauseum. Load W loads a word. For R0, what is that? That is the content of this memory location. Content in what sense? How big is it? Well, it's a word. Right here, I'm using W to load it, so I'm loading a word from the memory location given by taking R0 and adding 4 to it. And I'm loading that into R0. So immediately we know something interesting. We know source, destination. So it's, again, the opposite of the Intel world. Source, destination. Okay. Values are passed to and from functions and registers in order. So it's fast call. The first argument is going to be in R0, next one on R1, next one on R2, etc. That's his calling convention. And there's not much more to know, right? This is a little hypothetical assembly he's making up, a register transfer language in this case he's making up in order to give us some examples. And he gives you this initial decompilation. Well, we know this is called f, so we'll just call our function f. And only R0 and R1 are mentioned, so those are the only things that could be inputs. If we look at this, we'll see that R1 is used here, so it's live here. It's not modified here, so it's live here. It's not modified here, so it's live at the start. So it must be one of the inputs. What about R0? Well, it's set here, and it's set here, but it's set here based on the content of R0, so it's still live. So R0 and R1 are both live. From that, I can deduce that those are the arguments to my function. I hope that's clear. So this loads the word into R0. So he translates this into his C language over here by saying R0 gets the contents of address R0 plus 4 cast to be a word, which in his world is an int. So in ours, it would be 4 bytes. So I take this number, I cast it to be an integer pointer. So I'm saying this is an address of an integer, and then this goes and gets that integer. So when he was talking earlier about we're going to use casts, that's what he means. So then I multiply R0 by itself and store the result in R0. And I just translate that straight into this. Exclusive OR, I just translate straight into this. Return, that's fine. By convention, I return R0. So I'll just say return R0. So here's my initial RTL. And here is my first pass at an intuitive decompilation of that program. And I hope this makes sense, right? His intuitive example, aside from the weirdness over here, it should be fairly straightforward. This should look like normal. This should not look like anything painful. Maybe the pointer stuff, but you should be super familiar with pointers by now. So next, we can consider live ranges for each variable and give a new name, right? We want to convert this to static single assignment, single static assignment. I don't care, it's 2 S's, whichever one you like, because that's going to be how we can do subsequent work and analysis. So right now, we know we have overloading in the registers because we have something coming in R0, right? An address that we're adding to 4, right? This is an address, and getting a word and putting it in R0. Is that another address? I don't know. This was an address. I don't know what this is. So we may have 2 different things in R0 at the least over the course of this program. So we probably need to fix this using SSA. Another thing he points out is, hey, look, we have this expression right here. If we treat R0 as an integer pointer, which we're doing right here, because that's how it's used, then this expression could be converted to this expression. And again, this should not surprise anyone. This is how pointer arithmetic works, right? This is a number that I'm casting to be an integer pointer. Or I could cast this variable to be an integer pointer, which means when I add 1 to it, I'm actually going to add 4 because that's how pointer arithmetic works in C. And then I would dereference it. It's the whole thing. And this can, in fact, become this. So this looks like the first element of the array, the 1th element of the array, not the 0th. The 0th element of the array would just be the location R0. So this must be R0 sub 1. Okay, I hope that makes sense. So now we know that that could be R0 sub 1, and we can go ahead and make that change. And that's an improvement based on discovered type information. That's Mycroft's claim. He's giving us an intuitive example and walking you through it to show you intuitively how we can use type information to make our decompilation better. And in this case, we observed how this is being used and we were able to convert it to something that looks much nicer. All right, so I mentioned sequence points in here. Since we've named each value, we can substitute. We have to pay attention to side effects and sequence points. Okay, what is a sequence point? This is something that you would only need to know, I think, if you were writing a compiler, debugging a program, to writing a debugger, or you were reading the C or C++ language standards, because it's a big deal in C. You probably never heard of it because it's not something you should be having to think about a whole lot about. Maybe in the embedded world, but unless you're debugging or you're compiling, it's not that big a deal. A sequence point is a place in the program flow where the computation is regarded as stable. So if you use the Visual Studio debugger, and you open up the assembly view, and you're trying to like step through instruction by instruction, it won't let you do that. That's because it's going to force you to end your debugging, to freeze the debugger at a point at which the computation is regarded as stable. Because otherwise, you're going to see these weird intermediate results, and they don't line up with what's in the source code. And so Microsoft is there to prevent you from seeing the bad things. Basically, what it means is all the side effects of a prior computation have completed. Okay. Now, that means if there were values waiting to be written back to memory, they've been written. If there were intermediate values that were in registers that need to be moved, they've been moved. Right? All the different little pieces have converged, and you're in a stable state. And no side effects of subsequent computations have yet occurred. The C language standard makes heavy use of this, right? It's how you figure out what, like, pre-increment and post-increment, how to understand what they're doing when they're inside another expression, right? You have to figure out where is the stable part of the computation so I can figure out what's intended. This is all great. It's all great. Like everything that is, that makes a lot of sense and will help you understand programs, it's a lie. In reality, this stuff is, the compiler can output the information, but and it's going to do its best, but the processor can ignore stuff, right? The processor might not ever write a result back to memory. It just might never do it. It might not even write it to cache, right? Inside the processor, aside from the level 1 cache, there are write back buffers that hold information to be written back. And if those buffers never get, never have reason to be flushed, they'll never get flushed and you'll never write to cache. Weird stuff happens like that because in a multi-core world where there's contention for memory and cache, again, you're trying to do stuff faster and faster. And because of out-of-order execution, well, that blows this out of the water, right? Out-of-order execution can cause weird things to happen. But you shouldn't have to think about it at the level of the high-level language. That's a basic idea. So the compiler is going to do its best to make these guarantees and generate machine code that will honor these guarantees to the best of its ability to do so. The processor is going to do whatever the hell it wants to after that. Just life. That's how you get Spectre and Meltdown and things like that. So back to the intuitive example. So we have this now, and we can convert this rest of this into static single assignment. And when he does it, he adds little letters after it because he already has a number, right? So if it was R01, that would be hard to look at. So R0A is the updated R0. And that persists to right here when it becomes when we now have to use R0B, which persists to here, and we need R0C, which is what we return. R1 is never modified, so we never have to add a suffix to it. So this should be obvious to you as well, static single assignment. You should see how we arrived at this. Once we have this, I can do the thing I often do, which is I can do back substitution, right? So I can replace R0C with R1 exclusive OR with R0B, just plug that right in here. And so I wind up with R1 exclusive OR with R0B. What's R0B? It's R0A times R0A. Each one of those is R0 of 1. So it's R0 of 1 times R0 of 1. And I wind up with this expression right here, which I get by back substitution enabled by the fact that I have static single assignment over here. And there we go. And so this is the plausible source code, according to Mycroft, that we get from decompiling his initial examples. We start with this, and we wind up with this code right here. And it's plausible. Is this a plausible thing? Could you believe that? Sure, it's highly plausible. So Mycroft then goes ahead and says, okay, here's what we're really going to do. How much time do I have? I have no time. We're almost done for the day. I'm going to take each instruction in my register transfer logic, and I'm going to give you a set of mathematical constraints associated with that. So if I move R4 into R6, so I keep getting this the other way, R4 into R6, I'm going to require that those types be the same. That's different from Steensgaard, right? Steensgaard would have said, no, I've got to invent a partial order and do other stuff. Mycroft is having none of that, right? If I'm sticking one of these and one of these, they got to have the same type. And when I do this, right, when I have a load word where I have some offset from R3 and I put it in R5, then the type of R3, that's what T3 is, type of R3, which is a pointer to memory, which at offset N has something of type of R5, right? So this is a lot going on here, but we don't know or care what the type of R5 is, so we don't have a constraint for R5 over here because we don't have enough information to make one. But we do have information about R3. We know it's being used as a pointer to memory holding something that gets put into R5, so that's whatever the type of R5 is. XOR is a little easier. We just assume they're all ints, which is maybe a dangerous assumption, but that's what we're going to assume. Add, well, okay, here he makes some concessions. He says, well, it could be a pointer to something. In this case, he puts alpha in here as a type variable. So this could be a pointer, and that could be an int, and the result would be a pointer. Or the first thing could be an int, the second thing could be a pointer, and then the result could be a pointer, or they might all be integers. Right? It's unlikely that they're both can be pointers. Adding two pointers together would be weird. But adding a constant to a pointer, or an integer to a pointer, that's normal. Okay, so it gives you his type constraint like this. Here's what I expect. And then the other ones, same sort of thing. It should all be readable to you by now. It should make sense. Here we just stick number 42 in R7. That must be an int. Here we stick 0 in R7. It could be an int, or it could be a pointer, right? Because 0 could be null. So here we have a weird case. All right. This one is one to call out because it's kind of weird. There's a trick going on here. And the trick is I'm just adding these two together. And so if I wrote R5, R0, if I wrote this, it'd be the same as if I did this. Right? I could reverse them because addition is symmetric. It's commutative. So there you go. So that's why over here he has an or, right? Because that could be an integer, right? T5 could be an int, or R0 could be an int, right? And so we have this case where R0 is an int, this case where R5 is an int. The other one has to be a pointer. And we're going to assume it's to an array of things of type T3 because we're treating it as an array. This weird commutative trick with the array indexes, that works in C. Should give it a try. All right. New homework due April 20th. It's up on iLearn. I will upload my solution to blocks and attach it to the homework up there. So now we're going to try to visualize the structure of whatever program we want to analyze. And so you're going to take your program and modify it. Given an unknown elf binary, identify the basic blocks, and now you're going to identify the connections between them and generate a graph. Now, not every connection. We're not going to deal with the calls in here. But what we are going to do is we're going to find main or the entry point. We're going to find the basic blocks, and there are going to be some different outcomes. And I'm missing one in here because I was trying to edit the slide and I think I removed it in my addled state. The block flows directly to another via a jump, or it might flow directly into another because that's where two basic blocks got split. So at the end of each basic block, you should be able to answer the question, what is the next block in the flow? Okay, and it will either be a single block, like this, or it might be one of two different blocks because you ended with something that was a branch. Or it's something else. In that case, we don't know. Right? Could be a jump to something we can't figure out. Could be returns. I don't know what that is. Could be a halt. You know, who knows? So either it flows directly into another block, or it flows into one of two different blocks, or we give up. But this allows us to build a graph. Okay, and we're going to use GraphViz to build that graph. If you're not familiar with GraphViz, there's a link here. It's just a graph visualization tool. It takes stuff like this, it takes code like this, and generates this. And so we're going to be able to visualize our program structure. And so we're going to use dot, which is what the language is called, and just write this to standard output. You can render this whole thing by using dot. So if you go and get the GraphViz executable, you can just run dot on it. It may already be on your system. Just have to take a look. Here I generated a PNG. You can generate PostScript or other stuff with it, and you can give the output a name. You can call your program graph.py. It's not going to do this. It's just going to go ahead and generate this. So this is the address of a basic block, and this basic block has two possible follow-ons, right? It might flow into the next instruction, which is what this lower one is, or it might branch ahead to a later instruction, which is what this top one is. And you'll just build that whole structure for your program and turn it in. Next time, more Mycroft. We just scratched the surface and began to get into it, went through the intuitive example. Next time, we'll actually get into the meat of it. You might consider reading the paper. Don't trust my bad explanation of it. Read Mycroft's bad explanation of it.